PCB Foundations, by Paul Taubman and Sean Kelly. Presented by 9.Connects. Chapter 4. Design for DFX. 4.1. Introduction. In the PCB design flow, it should be understood how the manufacturing process works to get the right end product before designing for it. In fact, this philosophy of designing for something, DFX, is what we are going to investigate further. The two most important design for philosophies are DFT, design for test, and DFM, design for manufacturing. Think of the process as pouring concrete. Once you start mixing in the water, you have a limited amount of time to manipulate the concrete to the desired shape. Once it is hardened, breaking up the concrete is an effort in time, cost, and labor. This analogy applies to the PCB design process. The design phase is when you have the flexibility to move things about, to accommodate the manufacturing process, or to add features to accommodate the testing of the device. This is when the cement is wet, if we are keeping with our analogy. Once we move into the manufacturing process, options are limited. Our proverbial concrete has set, and we must work with what we have, or pay for breaking it up and redoing the concrete. 4.2. What are we designing for? There are a number of different design philosophies. DFE, design for environment. Design for the conditions in which the circuitry must operate. This could be a large range of temperatures, humidity, vacuum, radioactivity, high pressure, etc. For example, electronics that monitor a nuclear reactor must be designed to handle radiation. DFQ, design for quality. Design with consideration of longevity, or robustness, especially in situations in which failure could be catastrophic. For example, the electronics of an aircraft have to be designed for quality. DFC, design for cost. Design with consideration for keeping to a minimal cost, while providing a product that meets the needs of the customer. For example, think of a McDonald's Happy Meal electronic toy, that needs to be produced in millions with a cost that does not require the price of the meal to be increased. DFT, design for test. Consideration given to testing the product for debug if in a prototyping stage, or for yields in a production stage. For example, a product like a smartphone needs to be tested prior to shipment, to minimize field failures. Failures experienced by the customer, due to no fault of their own, have an impact on the company's reputation and branding. It is also an added expense to remedy the issue, and prevent customer dissatisfaction. DFM, design for manufacturing. Designed with the intent of production, with minimal manufacturing bottlenecks usually caused by special modifications to the fabrication or assembly process. For example, if a board has connectors on adjacent sides, the assembly process will have to be modified, since the board is generally held by clips on parallel sides during the assembly process. These philosophies are not mutually exclusive, and in fact, it is wise to design while considering all of them. It is a matter of prioritization of the philosophies. For example, if we are building a rocket to land on Mars, the top priority is DFQ and DFE, with DFC still playing a major role. DFT and DFM are critical in all designs, regardless of the priorities given to other design philosophies. The failure to implement both DFT and DFM comes at a cost in the form of respins, budget hits, schedule hits, and the possibility of project cancellation. 4.3. Respin implications. Consider the following implications of a respin. 4.3.1. Time loss. A respin normally takes 2 weeks or more, depending on the severity of the issue. Even for a fix that does not require an entire copper rerouting of the board, consider all the tasks that need to be done to get the design back into manufacturing. This includes, but is not limited to, meetings and emails to discuss the plan of action, and to point fingers. Research to find a new component, if replacing an obsolete component. Library modifications to create or correct a symbol and/or footprint. PCB layout modifications, and any subsequent copper rerouting. Regeneration of the PCB documentation. Once the corrections have been made, and the documentation has been regenerated, the design is now at the mercy of the fabrication and assembly schedules. Granted, they may be able to accommodate you, but there is a premium added for faster turn times. Lastly, do not forget that shipping time, weekends, time zones, and holidays, both in your country and the country that may be performing the manufacturing, are also stumbling blocks to the schedule. 4.3.2 Monetary cost. Cost comes in the forms of labor, services, materials, and time to market. The most immediate monetary loss comes from the scrapping of boards which were fabricated and possibly assembled to some degree. Even if the designer is salary exempt, meaning that they do not get paid overtime for extra hours worked, money is being lost since their effort is directed to a problem with the current design, rather than developing the next design. For accounting purposes, companies generally allocate funds to a project which include the labor costs. Even though the designer still gets their paycheck, the project budget gets hit severely. For most projects, by the time the project gets to manufacturing the first time, the funds for that project are most likely depleted. 4.4 Thinking ahead. The philosophy behind DFT and DFM is simple. Rather than designing for the task at hand, one designs for the processes that lay ahead as well. While this may sound logical and intuitive, it is not easy to implement, especially if one does not have a responsibility or control for the processes that come later. There are things that need to be prepared in earlier phases of the design, that have a monumental impact on the later design stages. Consider the following examples. A footprint that was not carefully drawn at the beginning of the project could result in the scrapping of fabricated boards weeks later. A bill of materials that was not vetted immediately upon the completion of the schematic design may be harboring components that are obsolete, thus causing the scrapping of fabricated boards, a scramble to find similar components, and a good deal of effort in the libraries, schematics, and layout of the design. In both examples, the failure of earlier processes to consider the process down the road will lead to respins and delays in product releases. There are thousands of decisions, and dozens of subprocesses preformed in making a PCB. Will something be overlooked? Yes. Will something not work upon power-up? Possibly. Will there be any debugging? For sure. In short, expect issues when a board rolls off the assembly line for the very first time. The way to deal with this is to be prepared. The old saying holds very true: expect the worst, and hope for the best. 4.5 Design for test. Describing the DFT process would take an entire book to fully define the techniques and practices. As such, this section will simply be an overview of DFT, to describe some of the key concepts and equipment commonly employed. It is important to know how the assembly process works, so that intelligent decisions are made during the PCB layout, to accommodate the assembly equipment and the visual inspections. In fact, visual inspection is considered a test. Similarly, the ease, or difficulty, of testing is highly dependent upon the accommodations made on the PCB layout. These accommodations include, but are not limited to: device separation/spacing requirements, height restrictions, device alignments, test points. Fortunately, if one considers the needs of the assembly pick and place machines and the visual inspection in their design, the effort to accommodate testability already has a good starting foundation. Test equipment accessibility is the most significant issue when it comes to testing. This is not too difficult when the boards are bare, since there are no obstructions. After a board has been populated with components, the ability to test obviously becomes more difficult. Regardless of the type or style of equipment, there is a physical connection that must be made to exposed metal of the board. This contact can be exposed copper on the board, such as test points, the solder surrounding the leads themselves, or the pins of the connectors, Note, placing any probes on the leads themselves is not advised, due to the ease of bending and/or shorting a lead to another. In addition to spatial accommodations of the components on the board, the designer should consider the use of test points. Test points do not have to be an installed component on the board, though test post type devices make it easier to hold or latch a probe to a signal. A test point can simply be an area of exposed copper on the signal trace, large enough to accommodate the probe. By providing test points, we avoid the need to place probes on delicate component leads. Generally, test points are via structures that are fabricated into the board. If large enough, the barrel of the via allows the tip of the probe to stay in position. In high-speed design, the test point may only be a surface mount pad, to avoid an antenna or a voltage reflection point in the signal path. If one desires to perform rapid testing, and the design is slated for high-volume production, test pads or test vias should be placed on a fixed grid. Be careful not to place them too close to the solder pads of the device, because they will leach away solder from the device's solder pads. Like the lands of the footprint, the test points are exposed metal. 4.6. Test types. There is a plethora of tests that can be performed on a board. Much of the testing has to do with the design philosophies that are being embraced. Some of the more common tests are discussed below. As for what tests are to be performed, one must lean on the design specification for guidance. This will be covered in more detail in a later chapter. 4.6.1. Continuity testing. Continuity testing checks the connectivity of each signal trace. The most common test is the opens test. This is a basic test in which an ohm meter is connected to the opposite ends of the signal trace. A resistance value should be detected. On a bare board, this resistance should be less than an ohm. If an infinite resistance is detected, the board needs to be investigated for an opening in the copper. Continuity testing becomes more difficult when components are on the board. This is due to the charging of the capacitors and secondary paths, due to the resistors in the circuit. Shorts testing is also part of the continuity testing. This is to ensure that unrelated signal traces are not making contact. This includes testing for power shorts. All the continuity tests mentioned so far are performed without power being applied to the board. The smoke test is performed when the populated board is being powered up for the first time. This requires monitoring of the lab equipment's voltage and current meters, to ensure that the board can achieve the desired voltage levels and current draw, while initially using a power supply in a current-limited mode. Both fabrication and assembly operations may perform continuity tests to ensure the quality of their service. In fabrication, continuity tests are performed on the bare board, PWB, for opens and shorts between signals. This requires a netlist to know the connectivity that is supposed to exist between the pins of each component. These are also referred to as lands. Assembly also performs continuity tests, however, they have the additional burden of dealing with components that are already installed on the board. Therefore, assembly must be strategic about interfacing with the board's exposed metal, without damaging or diminishing the integrity of the components. 4.6.2. Functional testing. Functional testing is simply that, testing the functionality of the board. This testing can be handled by either the assembly house or the design team. In many design flows, the company's design team will test and debug the original prototypes, and then develop a test plan for assembly, if the boards are being mass-produced and assembled. This plan generally includes a procedure for testing and any code to determine the pass-fail criteria. Full functional testing is one of the most comprehensive tests that can be performed, but it comes at a higher cost for test equipment, in addition to the process bottleneck it causes in the time it takes to test each board. Functional testing can identify engineering defects as well as manufacturing defects, down to a single test node. This is extremely useful when prototyping a complex board, or when rework is a viable option for the board. In many cases, the development of the test equipment and test program run in parallel with the board design process. Therefore, it is important to include the test team when it comes to the PCB design flow. In fact, on many boards, half the design process will be spent on testing the design against the specification, and debugging those functions which are not working as expected. Woe to the program manager who does not account for the time necessary for testing a PCB in their schedule. Regardless of who handles the test, DFT must be built into the design. Otherwise, one may make it impossible for the assembly house, and extremely miserable for the design team to test the board. If an assembly house declares no bid on functional testing, that's a strong warning sign that the board is not test-friendly. Functional testing can be performed on a chip, board, or system level. On a system level, the testing is performed with the PCB interacting with the rest of the product that it was designed to support. This testing is performed after the board has been tested in an isolated state to ensure that it will not electrically damage the rest of the system. Board functional testing is the act of stimulating the board using the peripheral connectors. It is treated as a black box, meaning that the test is simply determining if the output received correlates to the inputs being provided. Those who are testing may not know anything about the circuit, nor are they always privy to that information. In this situation, custom hardware may be needed to provide signals for certain tests. In many large aerospace firms, and in companies that make large systems, an electronic product being designed includes both the end product and the test rig for several reasons. The team that designs the PCB is not privy to the rest of the system. It could be confidential. It can also be that the system is very large and complex. Such details are not necessary for meeting the end purpose of the design. In many cases, the PCB is for a system which has not been completely assembled or developed. A test rig allows for a test environment that mimics the system. The test rig will likely become a part of the production process. If not the rig itself, the procedure and code of the test rig is ported over to the production process. All new product is tested on the rig, and defects can be debugged on the rig. If the board is not functioning as expected, those who are prototyping the board begin the debug process. This term comes from an incident back in the 1940s, in which a moth caused a malfunction in a military computer, known as the Mark II. It should be noted that it is extremely rare for a board to come up and operate without some issue. Time for testing needs to be allocated so that any issues can be investigated. Issues can range from trivial to complex, and everything in between. In most cases, prototype boards are tested bottom-up, meaning that the board is systematically brought online, and individual core functionality, like clocking and reset, is checked, prior to testing the board like a black box. Component testing is usually performed on complex digital devices, such as microprocessors, DSPs, digital signal processors, FPGAs, field programmable gate arrays, and any chip that contains a JTAG port. JTAG, which stands for Joint Test Action Group, was a group formed in 1985 to address testability on digital boards. During that time, most digital boards were stuffed with dual inline packages of discrete logic gates. The original concept of JTAG was to have additional circuitry and pins on each component that would allow it to be daisy-chained to the next component. There are 4 pins associated with the JTAG port used for testing. TDI, test data input. TDO, test data output. TMS, test mode select. TCK, test clock. The test performed is known as boundary scan, and consists of a series of digital signals that are fed into the TDI port of a device, while monitoring the TDO signal of another device for continuity checks, signal integrity checks, and propagation speed. The advantage of boundary scan is that the test is very fast, and can identify defective boards quickly. The disadvantage is that there is no failure feedback below the board level. In high-volume production, this is acceptable, since removing a bad board from being packaged and shipped is more cost-effective than trying to debug and fix a board. In the 1990s, there were rapid changes in the number of transistors being used in a single IC chip. In 1965, Dr. Gordon Moore of Intel noticed that the number of transistors found on a typical silicon chip seemed to double every 2 years. This became known as Moore's Law. By the 1990s, the transistor count hit the knee of this exponent curve. Now, it is common to have tens of millions of transistors on each chip. This allowed integrated circuits to contain embedded memory, and the ability to put into a single chip what used to be done by dozens of discrete digital logic components. In addition, innovations in silicon allowed these chips to retain the information that was programmed into them by the user. This is known as non-volatile memory, meaning that the data in the memory of the chip is not lost when the power is removed. These chips are also capable of being reprogrammed electrically. In the past, erasing a non-volatile memory required chemicals or UV light. As a result, JTAG became synonymous with programming chips, rather than testing boards. The two tests that are still commonly used via JTAG port are boundary scan, within the chip itself, and BIST, built-in self-test. The BIST tests the functional logic blocks within the chip. For PCB design purposes, the circuit designer needs to provide the JTAG port, along with any required circuitry between the port and the JTAG pins. JTAG can still be used at the board level, but it does require the PCB designer to add this functionality into the design. In addition, only components that have JTAG ports can be chained together. To conclude, there are other tests, many of which assist in debugging, or to obtain analytical data such as propagation speed, operating temperatures, current draw, etc. 4.7. Test equipment. The following sections will focus on the test equipment more commonly found in the fabrication and assembly houses, rather than the design labs. 4.7.1. In-circuit test, ICT. ICT, in-circuit test, relies upon the use of probes, to make contact to the metal on the printed circuit boards. ICT testers can be programmed to perform the entire test mentioned in the previous section, plus some. There are two connection methods commonly used in ICT equipment, known as bed of nails and flying probe. A bed of nails is a large collection of spring-loaded probes that are fixed in place. When through-hole components were the standard, a bed of nails test on a 2.54 mm, 100 mm, grid was the arrangement of choice. Even today, the bed of nails test is viable if the PCB is properly designed with sufficient test points to test the PCB functions. Since most boards are now populated with SMDs, and designers need the freedom to place components as necessary to accommodate the board real estate, the flying probe method is more commonly used. Whereas the probes in a bed of nails are set in a fixed position relative to the board, the two flying probes are on a plotter-like device that can move in any X, Y, and Z direction. It is programmed using the Gerber, pick and place, and test point files. These file types will be discussed in detail in later chapters. Devices with lead spacing down to 0.635 mm, 25 mm, can be tested with flying test probes. Spacing of 1.27 mm, 50 mm, is almost the norm for today's device pin spacing. 4.7.2. Manufacturing Defects Analyzer. An MDA, Manufacturing Defects Analyzer, also uses the flying probe approach. The MDA does a subset of what ICT can do, but was specifically designed to increase test throughput. Its primary purpose is to catch manufacturing defects, such as pin leads not making contact to the board, or any other non-continuity condition. 4.8. Test cost. In this chapter, the cost of test has been alluded to several times, and is far more substantial than most designers realize, or program managers take into consideration. Much of this cost is in terms of schedule. The time it takes to test is equal to the time it takes to design the board. It is rare that a board powers up and functions without some level of debug. Anytime a new component has been introduced to a product that has not been used in the past, there is a learning curve. The datasheets are not always correct, and sometimes the components have flaws in the silicon that do not perform as advertised. And, believe it or not, sometimes the circuit designers even make a mistake. Testing requires a lab, and lab equipment is expensive. This is why the test engineers need to be included in the specification writing. They can tell immediately what testing can be done with equipment in-house, or if they need to procure or make test equipment. 4.9. Chapter Summary. In conclusion, when it comes to test, the assembly and fabrication houses can only work with what was given to them. It is important to know what equipment they may have, what files may be of use to them, and if any JTAG configurations have been designed into the PCB. Even if the design test does not opt for assembly test beyond basic continuity checks, assume that the board will need to be tested by the design team, and that issues will arise. DFX is an important consideration in the design process. Failure to recognize it can lead to respins and other delays to fix it. Test is not a single operation in PCB assembly. Normally, it takes more than one test technique to ensure the PCB is manufactured correctly with no defects, and the PCB is functional from the design and engineering standpoint.